welcome to True Projects. In this video, we are going to explain about the project that is NIDS VSB Network Intrusion Detection System for VANET using Spark-based big data optimization and transfer learning. So before getting into the execution, first let us understand what is the project about. Now think about how modern vehicles are becoming smarter with all the advanced technology built into them. They are constantly communicating with each other. They share real time data about road accidents, traffic congestion, and also even accidents. So, this whole setup is called Vehicular Ad Hoc Networks, that is called VANet. And it is a game changer for all the improving road safety and traffic flow. But here, the problem we have is that because of all the communication happens over wireless networks, it is pretty easy for hackers to mess with it. They can intercept messages and send false traffic alerts or even launch attacks that disrupt the entire network. Imagine a hacker injecting fake accident reports into the system. Drivers might change their routes unnecessarily, or worse, an emergency response could get delayed because of misleading information. So to prevent all of this, to prevent all these kinds of attacks, we have network intrusion detection system, that is NIDS, which monitor traffic and detect suspicious activity. But the issue is that traditional NIDS aren't built to handle the massive and constantly changing data that VANets generate. They usually rely on predefined rules or past attacks signatures, which means they struggle with detecting new and evolving threats. Plus, with so much data flowing in real time, processing all of it quickly and accurately is huge and also a big challenge. If the system takes too long to detect a threat, that damage might already be done before any action is taken. So, the current so the problem with the current network intrusion detection system, that is NIDS, is that they aren't always reliable. One of the biggest issues is false positives. Basically, the system keeps flagging normal traffic as potential attack. So imagine getting constant alerts about threats that don't actually exist. After a while, people just start ignoring them, which defeats the whole purpose of having a security system in the first place. On top of that, these systems aren't built to handle the massive amount of data that VNets generate. As number of connected vehicles increase, traditional NIDS start to struggle, making it harder to keep up with all the network activity in real time. And now, here where the things get even trickier is that attackers are getting smarter every day. They're not just using the same old hacking techniques. They are constantly evolving, tweaking their methods to slip past detection. A lot of existing machine learning and deep learning models based security systems try to identify these threats, but they often fall short because they don't understand the deeper meaning behind network patterns. Without semantic analysis, basically the ability to basically to analyze the intent and context behind network behavior, these systems end up missing some of the more sophisticated cyber threats. It's like trying to understand a conversation just by looking at individual words rather than full sentence. So you're going to miss out a lot of important details. So what is the solution? We need an intrusion detection system that is not just fast and scalable but also adaptive. It should be able to analyze large amount of data efficiently, learn from new attack patterns, and also incorporate deeper analysis techniques to detect even the most advanced threats. So here the idea of this project is to make the network intrusion detection in VNets smarter and faster by using big data optimization and transfer learning, which are advanced technologies. So first, think about how much network traffic data is constantly flowing in a VNet. Vehicles communicate with each other, they send updates about traffic, road conditions, etc. So processing all this heavy data efficiently is challenge, and that is where Spark comes in. So Spark is great at handling large scale data about because it breaks it in smaller chunks and process them in parallel, which makes everything faster and more efficient. Once the data is pre-processed, we use word to vec, which is a technique that helps to convert this raw network data into a more meaningful form. Instead of just looking at the data as bunch of random numbers, word to vec understands the relationship between different traffic patterns. This is called semantic analysis. Kind of like how it would understand word meanings in a language model. So this means the system isn't just reading numbers but actually understanding patterns. It is learning patterns in how attack happen, making it better at spotting the threats. So once the data is converted into meaningful features using word to vec, the next step is to extract deeper insights from it. So that is where convolutional neural network comes in. So that is called as CNN, convolutional neural network. This CNN is used for image processing, but here they are being used to identify patterns in network traffic data. Think of it like a powerful filter that picks out the most important details from the data, making it easier to spot the intrusions. After CNNs extract these refined features, they are passed into a stacked ensemble learning model. So it is passed into a stacked ensemble model, which is combination of multiple classifiers working together. And one of the key classifier in this step is random forest, which is great at making prediction by analyzing different patterns in the data. So instead of relying on a single model, this approach combines multiple models to improve accuracy and makes the prediction system more robust against different types of cyber threats. And the key advantage here is efficiency and scalability by using Spark for big data optimization and transfer learning for improving feature extraction. The system can process large volume of network data quickly while maintaining high detection accuracy. This ensures that VNet security stays strong and also reliable even as cyber threats evolve. So this is the proposed system. Now moving on, to further improve the performance of this project, we have incorporated voting classifier, which is an ensemble model that combines decision tree, random forest, and XGBoost. So each of these models are fine-tuned with optimized hyperparameters to maximize their performance. The voting classifier works by evaluating the predictions of all the three models, that is decision tree, random forest, and XGBoost. So what it will do is the voting classifier works by evaluating the predictions from all three models and selects the one that performs best based on the accuracy. This ensures that attack detection system doesn't just rely on one algorithm but rather benefits from the strengths of multiple models, making it more reliable and robust in identifying cyber threats in VNets. Additionally, on top of that, a front-end interface is developed using Flash framework, which allows users to interact with the system easily. This include user authentication, ensuring that only authorized users can access the system. This addition makes the intrusion detection system more practical and also user-friendly, which provides a secure and efficient way to monitor and also analyze network threats. So this is the extension part. Now, to implement this project, we have followed the steps mentioned in the flow of work. So let's understand each of the steps. First, what we have done is we have loaded all the necessary Python libraries for data processing, visualization, model training, and Flask-based frontend. Then comes exploratory data analysis. So here we perform an initial analysis of the data set to understand its structure, distribution, and key insights. Coming to data visualization. So here we use graphs and charts to analyze network traffic patterns and also attack distributions. Then comes data pre-processing. So here we handle missing values to ensure data and integrity, that is data consistency, and we convert all the categorical variables into numerical representations. And then we normalize numerical features for uniformity across the data set. Then comes extraction with the word to vec, that is feature extraction. It is feature extraction. So here we convert traffic features into numerical representations and then we apply word to vec to transform sequential network flow data into meaningful vector embeddings. And then we capture contextual relationship between different network attributes. Then we define and configure machine learning model for attack classification and we train machine learning models. All the optimized hyperparameters are tuned. We train the models using optimized hyperparameters to improve the performance. And then we evaluate all of them using metrics that are accuracy, precision, recall, and FN score. And coming to the part of front end, here we have built a user-friendly interface for interaction using Flask framework. And we have also implemented registration and login with SQLite database for secure access. And users, they will be able to provide feature values as the input in the front end. And it will be pre-processed at the backend. It will be fed with a train model. Finally, outcome will be displayed through the front end of the application, predicting the attacks. And this is the implementation part. That is how we have implemented the project. Now moving on to the algorithms used. So these are the algorithms used in this project. And now coming to requirements. To implement, we need basic requirements, which are hardware and software. So coming to hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And software requirements are application of Python, front-end framework of Flask, back-end framework Jupyter Notebook, database SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. This is the overview of the project. Now let's execute. So to execute, open the code folder that contains source code file. So let's open the code folder of the project. So these are the source code files in the code folder of the project. Let us understand each of them. How will they be used in this project? So this is the dataset folder in which we have dataset. So we have used CIC IDS 2017 dataset. So let's open it. So this is the dataset, and these are all the attributes that we are using in this project for predicting the attack. And from all these features, we will be selecting the most important ones. Let's close this. And this is the test data that we will be using in the front end to do the prediction. And in this model folder, we have the algorithm information that is stored in .hpy files, numpy files, and pickle files that will be loaded into the project or during runtime of the application. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And here we have templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here we have main.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. This is the notebook.ibvanb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And this is the Windows batch file. Instead of executing this project through command line interface, we have created this Windows batch file. Now we need to double click on it to execute. So double click on it. Here you can observe, right, main.py file is compiled. Now this command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the Flash framework, application will host, Flash framework will host the application at the default address, which is the local host and the port, unless configured differently. So just wait for a while. File is being compiled. So here Flash framework has hosted the application at this address. This is the local host. This is the, 127.001 is the local host and 5000 is the port. Now copy this local link provided by the Flash framework and paste it into any web browser. I've copied it. I prefer Google Chrome, so I will paste it in that. Paste the link here. Click on enter. So before clicking on enter, type index and click on enter. So this is the web page of the project, which is displayed in the browser. This is developed using Flask framework. So click on admin, provide your username and the password. Now click on login. We have logged in successfully and we are redirected to prediction page of the project. So let's click on predict NIDS attack. Here we can see choose file button, right? We need to click on that for uploading the test data. So let's click on that. So click on choose file, select the test data, click on open, and now click on submit. So before clicking on submit, let's see what do we have in that file. So let's open dataset, open test data. So these are the different test cases that we are giving as input. So we have total 14 test cases. Now we will be giving them as input, and these are the parameters. Let's understand each of the parameters. So the first one we have is destination port. It is the port number on the destination server receiving the traffic. And then we have flow duration. So here we have the total time in microseconds for which communication between source and the destination took place. And here we have total forward and backward packets. So here these are the total number of packets sent forward and also in backward direction. And then we have total length of forward packets, and here we have total length of backward packets. So here we have total number of packets sent. These are the total number of bytes sent from the forward direction and also from the backward direction. And then here we have forward packet. So here we have forward packet length max, and here we have forward packet length mean, and here we have mean and standard deviation. So here we have forward packets max. That means that it is the largest packet size in the forward direction. Min is the smallest packet size in the forward direction. Mean is the average size of the forward packets. Standard deviation is the STD is the standard deviation of packet size in the forward direction. And then we have backward packet length, that is backward packet length max. And here we have backward packet length min, and here we have mean and standard deviation. So here we have same as forward packet length, mean, median, standard deviation. Here also we have for backward packet also, but it in the reverse direction, that is in the destination direction. Forward is the source and backward is the destination. And then here we have flow packets. So these are the number of packets transmitted per second in the flow. And then here we have flow IIT mean, flow IIT standard deviation, flow IIT max, and flow IIT min. So IIT, it refers to inter-arrival time feature. So it measures the gap between consecutive packets in a flow. Here we have for mean, I mean flow IIT mean value, standard deviation value, max value, and minimum value. Accordingly, we have forward IIT min, forward IIT total, forward IIT mean, and also we have standard deviation, forward IIT max. So these measures the gap between forward packets only. And then accordingly, we have also backward packet length. So here we have for backward. We have backward packet total, backward IIT mean, backward IIT standard deviation, backward IIT max, and backward IIT min. And then we have different flags here. So here we have different flags, that is FWD, PSH flag, and here we have BWD, that is backward PSH flag, forward urge flag, backward urge flag, forward header flag, and backward header flag, backward header length. Sorry, up to here we have flags. So these are the flag values. So here flag is nothing but it is a TCP control mechanism. Forward PSH flags and backward PSH flags indicates the push flag is set in the forward backward packets affecting the data flow urgency. Then coming to urge flags, that is forward urge flag it may be, or it may be the backward urge flag. It indicates the urgent, that is URG flag is set, meaning high priority data is sent. And then here we have forward header length and backward header length. So it is the size of the headers in the forward and backward directions. And then we have forward packets and backward packets. It is the rate of the packet sent and received per second. And then we have minimum packet length, max packet length. And here we have packet length mean, packet length standard deviation, and packet length variance. So here we have all the minimum packet length, maximum packet length, mean, packet length, standard deviation, and packet length variance. It provides the statistical measures for the packet size in the flow. Then here we have FN, that is FIN flag count, SYN flag count, RST flag count, PSH flag count, ACK flag count, URGE flag count, CWE flag count, ECEF flag count, and then we have, yeah, that's all. These are the flag counts. So these are the TCP flag counts. So these track the occurrences of the different TCP control flags which are useful for detecting malicious behaviors. So these flags are very important. And then we have down up ratio. Here we have down up ratio, average packet size. So your down up ratio is ratio of download to upload the traffic. And then we have average packet size. It is the average size of all the packets in the flow. Then here we have average forward segment size, average backward segment size. So it is the average segment size in forward and backward directions. And then we have forward header length, forward average bytes, forward average bytes or bulk it is. And then we have forward average bulk rate. So here it measures the efficiency of bulk transfers in the forward direction. It is the average of forward average bytes bulk. And then we have backward average bytes. So here we have backward average bytes, backward average packets bulk, and here we have backward average bulk rate. So this, it is same as forward. That means it measures efficiency of bulk transfers in the backward direction. Then we have subflow forward bytes, that is forward packets, and then we have subflow forward bytes. Here we have subflow backward bytes, subflow backward bytes. I mean, here we have subflow backward packets, here we have subflow backward bytes. Here, subflow forward packets and subflow forward bytes are the count of the packets and bytes sent in the subflows, that is, smaller segments of the traffic. And then here we have initial win bytes. So here initial win bytes in the forward direction, in the backward direction, and then yeah, we have only these two of initial. So it is the initial TCP window size, that is a buffer size for receiving the packets. And here we have act data backward, I mean packet forward. So it is the number of packets carrying actual data excluding control packets. Then we have minimum segment size forward. It is the minimum segment size seen in the forward direction. And then we have active mean. So here we have active mean, active standard deviation, max, and min. It measures how long the connection remains active before being idle. And then here we have idle mean, ideal standard deviation, idle max, and idle min. So it measures the duration of inactivity in the connection. So this is all about the features. Now let's submit it. So these features will be given as the input to the application, and then they will be pre-processed at the backend. Finally, output will be given by the application. Click on submit. And here we got the prediction. So the first case, so this is the first case that we have given. For this case, it has been predicted as it is web attack. Here it has been predicted as web attack XSS. And here for the second case, it has been predicted as web attack. It is a web attack. It is SQL injection attack. It is. And then for this case, web attack has been predicted, and that is brute force attack. So here brute force attack has been predicted. And for this case, there is no attack. That is why it is predicting it as benign. And for this case also it is the same because it is predicting benign. And for this case also it is the same case. And here also it is also predicting benign because there is no attack in that case. And here in this case, attack has been predicted, that is brute force attack. And here we have brute force attack predicted. For this case, brute force attack has been predicted. And here we have SQL injection attack predicted for this case. And for this case, SQL injection attack. So accordingly, for all the given cases, attack has been predicted. So this is how you need to execute. Now click on logout. In this way, just by giving input to the application, application will be predicting the attacks in the given data. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.